So these are two graphs of an exponential function, depending upon what our actual value of a is. Now, a greater than 1 is going to have our exponential function moving up as we go from left to right as our numbers increase. And if we have a number between 0 and 1, it goes down. Essentially, a number between 0 and 1 is some sort of fraction, some sort of rational number that's smaller than 1. And as we increase essentially the denominator, we get closer and closer to 0. So think of kind of like the function of 1 over x. That'll give you an idea of kind of how that works on the end form. All right, so I've got the domain here. The domain is all real numbers for an exponential. As you can see, the graphs are continuous without an issue. And the range is strictly greater than 0. It can't actually be 0. Okay, also you'll note we're looking for values between 0 and 1, not including 0, not including 1, and then strictly greater than 1. We take a value and raise it to the, take 1 and raise it to an exponent, we get 1 again. So that's why we don't use that. All right, so the inverse function for these exponentials is called a logarithmic function. And here are the properties, first of all, the definition and then properties of the logarithm. So let's look at the definition first. All right, so it says for x greater than 0 and a greater than 0, and a doesn't equal 1. We've already discussed a not equaling 1 because of the problems with that. So if you have y equals log with a base a, and this little guy here is the base, and that looks awful. Well, that little guy down there is the base. If y is log base a, if and only if x is equal to a to the y power. So there's a conversion that we can make when doing that. We have some properties down here, but first let's draw the log function. We'll say log base a. Since it's an inverse function, it's going to look, so this one goes through the point 0, 1, so this one will go through the point 1, 0, and it'll look something along these lines here. Remember, the inverse should mirror the y equals x a line. So we should have an imaginary line here that these are mirrored around. All right. So those are what the graphs look like. We have some of these properties here. Log base a of 1 is equal to 0 because if we look at this property over here, we're going to have our value, which in this case is 0, 1 is going to equal a to the 0. Well, anything to the 0 is 1, excluding 0, of course. But we don't have to worry about 0 because a cannot be 0. Our second property, log base a of a is equal to 1 because a to the 1 is a. That's no problem. Again, using that same thing that I've got highlighted. Our inverse property. So log base a of a to the x equals x, and a to the log base a of x equals x. So each of those kind of cancels out. And what I typically do, if I draw this, you can do a big canceling here or a cancel there, and you're left with the circled part. Okay? It's just a little shorthand that I typically do. And the one-to-one property is if we have log base a of x equal to log base a of y, then x must equal y. It's going to be a function. You're not going to have multiple solutions to one thing. Think of it as the vertical line test. That's what we're talking about here. All right, so I picked a couple questions from 5.2 to do. Well, I picked one from 5.2 to do, and I made an example. All right, so on page 376, they give us the instructions for the first set of questions that indicate that they want us to write the logarithmic equation in exponential form. So we're going to use that property that's highlighted up there. So what I like to do is that one-to-one property works as well for exponents. So this also works for a. If a to the x equals a to the y, that means x must equal y. That works as well. So I can take these and I can make our base is 4. So I take 4 to log base 4 of 16 equals 4 to the second power. Because again, log base 4 of 16 equals 2. Well, the log base 4 and the 4 cancel, and I'm just left with 16 equals 4 squared, which we know to be true. I've got another example. I'm going to work it out in the same manner. I'm going to use my base of 8 here, so I'm going to make 8 my a. So that's what we have here. Again, these cancel. And I'm left with 4 equals 8 to the 2/3 power. And we can solve for that. What this is, all right, so you're done here. But if you want to solve 8 for the 2/3, well, that's the cube root of 8 squared, which is the cube root of 64. Well, 64, not 6 to the 4th, excuse me. And 64 happens to be 4 cubed, so that's just 4.